The problem here, each of the three boys tosses a die once. Okay? Find the number of ways for them to get a total of 14. Let's solve this using the generated functions and all the necessary relationships therein. Now take note, for each of the boy, there are actually 6 possible results. Say for example, for boy 1, the results he would get would be 1, 2, 3, 4, 5, and 6. This is also true for the results boy 2 and boy 3 can get. Now, if we're going to represent this using generating functions, and take note, they are tossing each of their die once. That would mean for boy 1, it would be x once, because there's no way that he cannot choose any of this. Of course, also x squared plus x cubed plus x to the power of 4 plus x to the power of 5 and plus x to the power of 6. Okay, there's only one way for that possibility in choosing 6. One way in choosing 5, because the boy 1 also only tossing the die once. This is also true for boy 2, x plus x squared plus x cubed plus x to the power of 4 plus x to the power of 5 and plus x to the power of 6, as well as for boy 3. Another multiplier, x plus x squared plus x cubed plus x to the power of 4 plus x to the power of 5 and plus x to the power of 6. In short, for all of them, because we have, say for example, a fair die is tossed, so we'll have 1, 2, 3, 4, 5, 6, possibility of choosing all of these numbers once. And then again, there's no way that 1 to 6 will not be chosen in one of the possibility of tossing the die. This would mean, using these generated functions, for all of them is actually x plus x squared plus x cubed plus x to the power of 4 plus x to the power of 5 and plus x to the power of 6 with exponent of 3, because there are 3 boys and that is the number of possibilities for each of them. Now take note, we would like to know the possibility of getting a 14. The sum of that would be the a sub 14 paired with x to the power of 14. This would be equivalent to the coefficient of x to the power of 14, which tells us the number of ways to select 14. And 14 here is the sum of all those selections. Say for example, boy number 1, after he tossed the die once, he could get 1. And boy number 2, let's say for example, is 5. That's already 6, right? Say for example, for boy 1, after tossing his die, he got 3. Okay? And boy number 2, he got 6. That's already 9, right? So 3 plus 6 is 9. Therefore, the remaining boy should also get 5 to get 14. So the number of ways of combinations for that, it is actually the number of ways to get this 14. So to continue that, we will go to the necessary process where we can actually look for the possibility of the existence of x to the power of 14. Now allow me to factor x to this, because we have the greatest common factor for all the terms here being x. That would mean the first term will have 1, second term is x, third term is x squared, sorry, that's squared, plus, sorry for that again, squared, plus x cubed, plus x to the power of 4, and x to the power of 6 will be x to the power of 5, and both of these factors raised to 3. By power law, you will have here x cubed times 1 plus x squared plus x cubed plus x to the power of 4 plus x to the power of 5 raised to 3. Now, one might think that this is actually equivalent to a certain expression in this manner. You can actually write that 1 over 1 minus x, okay, raised to the power of 3. But take note, if we're going to look into this perspective, this is actually connected to the idea of 1 plus x squared plus x cubed plus so on and so forth. This is true for infinitely many terms following this specific pattern. But here, we ended until x to the power of 5. In short, we can invoke this. Take note of that. We can invoke this because it is true for the summation until infinity. Okay, that's for a definition of that. So what I would like to do here is this. Okay, so please bear with me as I'm going to give you another concept here, very important for the analysis. Of course, we know that this is already x cubed here, but So what would be this expression here? Let me rewrite that here. 1 plus x squared plus x cubed plus x to the power of 4 plus x to the power of 5. Looking at each term, 1, x squared, x cubed, x to the power of 4, x to the power of 5, they form actually a sequence. And since we are adding them, this is an example of a series, specifically a geometric series. Because when you look from one term to the next, we also actually have a common ratio, which is x. 1 times x is x, times x is x squared, times x is x cubed, times x, and times x. This is an example of a geometric series, specifically a finite geometric series. And we actually have a method of writing a finite geometric series. Now, for a geometric series, we can actually take the sum of this using a certain formula. The sum for actually the number of n in a finite geometric series is also taken as 1 minus r to the power of n over 1 minus r, or could also be represented as r to the power of n minus 1 over r minus 1. They are just the same. Let me use the first one because here our r common ratio is x, and there are 6 terms. That's actually our n is equal to 6. Just for this one, okay, don't be confused with the r later for the entire form, or n. So with that, I'm using the first one. The sum, or this one, can be represented by 1 minus x to the power of 6 over 1 minus x, as this is our form here. Now, with that, let's try to use this sum as this factor here, indicating that. So moving forward, you'll have this form here, x cubed times 1 minus x to the power of 6 over 1 minus x. But take note, this sum is actually raised to 3, so we still have raised to 3 here. So, going down, you have x cubed, and you will have here 1 minus x to the power of 6 cubed, and then you have here over 1 minus x cubed. Look at the denominator. This now patterns to a certain expression that can be written as 1 minus x raised to the power of negative n. So this can still be represented as x cubed times 1 minus x to the power of 6 cubed, and then 1 minus x negative 3. Okay? So this time, we can try to multiply this. That's very exact, as we have here the cube of that. As for this form, we will be using the equivalence of that expressed as 1 plus 1 plus n minus 1, okay, combination 1 for our x, plus you have 2 plus n minus 1, combination 2 for our x squared, until you have your nth term. You have r plus 1, n minus 1, combination r for our x to the power of r. We have already r here. Actually, that's the thing that we are trying to solve later on, x to the power of 14 specifically. So let me try to use first this one, okay, we'll be combining that later on, okay, to this expression here. So what happens here then is that, so we have here x cubed, and then the cube of this binomial expression. Using special products, we have 1 cubed, then you have here plus 3 times the square of the first term and the second term, okay, plus 3 times the first term and the square of the second term, and you have here plus the cube of your second term. Okay, that's it for its special products. You have here x cubed, and this is actually just 1 minus 3 x to the power of 6. You have this is the square of this, plus 3 x to the power of 12, and you have here minus, you have because add number exponent, x to the power of 18. Okay, which can be simplified when you distribute that to all the terms. This x cubed, okay, x cubed minus 3x to the power of 9 plus 3x to the power of 15 minus x to the power of 18. Okay, but this is actually sorry, not 18, plus 3, you'll have actually 21. Now this is just the portion including this one here, but since we have this form, which is actually for the nth term equivalent to that, this is actually multiplied to the summation, okay, with the following notation. For the r, we'll have r plus n minus 1, combination r, x to the power of r. Okay, making this as actually this one here, making this as the coefficient we're going to solve as we connect this two relationships here. So let me try to copy this and place it on our next page. Okay, copy that. I'm going to add a page here. Okay, we can continue on this side. If I'm correct, removing this and that, and then you have here D is equivalent to R plus N minus 1 combination R and X to the power of R. Again, our goal is for the coefficient to be paired with X to the power of 14 as the number of ways where the sum of the results for the 3 dice tossed would be equal to 14. Now, looking into this perspective, we can actually distribute both of this to all the terms here. So you will have actually here R plus N minus 1 combination R for X to the power of R plus 3. Because as you have R plus 3, then minus R plus N minus 1 combination R. Again, if you're confused with why do we use this and not the summation, because this stands for the rth term, okay? The rth term. We don't need the summation for all. We simply need to use the illustration. And of course, this is already identified in one of the generalizations in this playlist as A sub R, which is equal to R plus N minus 1 combination R. When we have situations like the number of ways of selecting R objects or distributing R objects in n distinct boxes, given that, of course, number of ways of distributing R objects in n distinct boxes. Okay, so we have this. That's why we have minus and then 3 X to the power of R plus 9. Okay, and then you will have here the next one plus 3 X to the power of R plus 3. Sorry, I forgot the multiplier. You have R plus N minus 1 combination R. You will have here 3 X to the power of R plus 15, and you have here R plus N minus 1 combination R for our given here, let's say negative, sorry, this is negative, so this is minus X to the power of R plus 21. So for this to be true, what should be done here is that, again, our target is X to the power of 14. For that to be true, this should also be equivalent to X to the power of 14, as well as this, as well as that, and here. So let's have here X. We have R plus 13 must be equal to the X to the power of 14. So our R plus 13 let's call it R sub 1 is 14. So our R sub 1 is actually equal to 11. Okay, next, for our next situation here, X to the power of R plus 9 must be equal to X to the power of 14, so that this will be counted as one of the components for our coefficient here for X to the power of 14. So R plus, or R sub 2 plus 9 is equal to 14, so you have R sub 2 is equal to 5. Then for the next, you have X to the power of R plus 15 must be equal to X to the power of 14. So this case, you will have here R plus 15 is equal to 14, R is equal to negative 1, and this time this is not possible because our R here cannot be negative, so this is not possible, not applicable here. This same goes with X to the power of R plus 21 is equal to X to the power of 14. R plus 21 is equal to 14, and you will have your R is negative 7, still not applicable here. What does this tell us? We only need to use the first two terms, having their specific R sub 1s and R sub 2s. Okay? For our N still, N equal to 3 as there are 3 boys who actually are playing the said experiment. So moving that here, so copying the first one is R sub 1 plus N minus 1 taken R sub 1 times your X to the power of this one here. Yeah, 14. That is actually now 14 for 11 plus 3. And this will be added, or subtracted rather, with R sub 2 plus N minus 1 combination R sub 2 for X, again, a power of 14 as we use here 5. I don't forget, there's actually 3. Sorry for that. Please don't forget the other multiplier here. This one, we have actually 3 times X to the power of 14. It will matter later on the product. So let's start with this. The first one, we have 11 plus 3 minus 1 combination 11, okay, X to the power of 14 minus you will have here 5 plus 3 minus 1 combination of 5 times 3 to the power of x to the power of 14. Factoring x to the power of 14, so you will have here, let's try to solve for this. So we have here 11 plus 3 minus 1 is actually 13, combination 11 for x to the power of 14, minus 3 times 5 plus 3 is 8 minus 1, 7, combination of 5, you have your x to the power of 14. Let's factor out for x to the power of 14, and the result here would be 13 combination 11 is actually 78, okay, minus 3 times 7 combination 5, that's actually 21. So 78 minus 63 x to the power of 14, so you will have here 78 minus 63, you will have 15 x to the power of 14. This coefficient tells us the number of ways. What was the problem? Not selecting. Number of ways for them to get a total of 14. The number of ways to get a total of your exponent 14. In short, the answer to this question is just simply 15. We're able to use that considering these relationships here. At the same time, the use of our final geometric series in the previous portion. Again, take note again, we're just using this because this stands for the rth term to just introduce x to the power of r. And then again, these were all made possible by the use of generating functions. Thank you very much for watching.